Okay, welcome back. So, in this section, we're going to be, in this video, we're going to be going over a very important but very, very confusing topic of these circuit analysis, and that is how do we name the topology of different op-amp circuits? This is something, I mean, this is just a hobgoblin of, this is just biggest source of confusion in this entire class is how do we determine if a circuit is series-shunt, series-series, shunt-series, shunt-shunt. And there's a couple of, so unfortunately everything is confusing about this process. The mechanism we use to determine whether the first term is series or shunt are different, and also the naming convention that's used for these differs from book to book. So I'm going to go over basically, I'm going to draw a circuit, describe how we tell how it's named for our book, and then I'm going to give you the circuit, I'm going to give you the same the name of that same circuit that's often used in other books. It's very, very confusing, and I apologize for it. I'll do my best to try to make this clear. I'll try to make this process clear in showing you how to derive the name for these different circuits. Okay, so first of all, so I'm going to first of all show you. Well, I'm going to build an op-amp circuit here. Okay, you might recognize this. This is the non-inverting op-amp configuration. So the how do we name this? How do we name this circuit? So we have. I'm going to write the name of this that our book uses, and then I'm going to talk about why it's that way. So this is a series shunt configuration. So I'm gonna first talk about basically where we get the term shunt from, the second term in this. So in our book, the way the naming convention goes is the last term refers to the method of sampling the output. The first term refers to how the input signals are combined together. And unfortunately, they're opposite with current and voltage sampling for these two. And I guess it makes more sense if we show a load here. Okay. So the naming convention here, we're going to start with the second name here. So in this case, the output that we are sampling, what we are sampling to provide feedback back to this op-amp is we're sampling this voltage here. We're sampling the output voltage, and to measure that voltage, we're sampling it, running it back through this feedback network. But that output voltage is also driving this load resistor. And so the idea here is basically, and this is true anytime we have an output that is a voltage, when the output is a voltage, we are sampling this voltage in parallel. That's always the way you sample voltage. Is if you have a multimeter, if you're trying to measure voltage in a circuit, and the circuit's doing its thing, what do? You connect the multimeter in parallel with that resistor to sample that voltage. So sampling something in parallel is a way of saying you're sampling it in shunt. That's the way the terminology is being used in that case. So essentially, anytime you are using the voltage output as your source of feedback to your circuit, that second term is going to be shunt. Now, so keep that in mind. If we sample voltage in shunt, we always put our meter in parallel with the voltage that we're trying to measure. Boom. If our output is a voltage that we're sampling, that second term is going to be shunt. Now, series is a little bit weird here. Series on the input refers to how this is being, whether or not this is being sampled in series or in shunt. So it's a little bit different because essentially here our input here is a voltage to our circuit. And so essentially it is, our op-amp is taking this voltage in series with the voltage here to produce this differential voltage. That is considered series sampling on the input. So basically, when we have a voltage input as the signal to our input of our amplifier, if the input is a voltage, referred to as series, even though a voltage at the output was sampled in shunt. So very confusing. If the input signal is a voltage, then it's called series. And you can kind of see that. You'll see that a little more when we get to shunt input circuits. You can kind of see shunt inputs. You do have two currents typically that are combining together to form the current flowing into the amplifier. So anyway, it's a little weird. Just try to follow this. I'm going to do my best to explain this. But in general, if your output's a voltage, that's considered a shunt output. If your input is a voltage, that's considered a series input. And I know that's weird, but that's the way it works out. You got to be careful too to know whether or not there is a series input. The best way to tell if there's a series input to an op-amp is say, if you have a voltage at the input, you can tell generally that it's series by saying, if I change that voltage up and down, does the actual voltage of the op-amp terminal go up and down? Right? There are some cases where your input is a voltage supply, but increasing the voltage supply doesn't actually change the voltage of these terminals. In that case, check to make sure probably what's happening there is your voltage supply is actually being converted to a current, and you're actually sampling a current input. So just that's a test. Okay, so this is a series shunt. There are other books. This is the way our book calls it, series shunt. There are other books that would refer to this as voltage series. So where shunt is basically saying, so basically what they're saying is we're measuring the voltage of the output and the input is in series. So some ways of describing this type of circuit are going to, first of all, say whether or not you're sampling a voltage or a current at the output, and then they will talk about how the input is configured at the amplifier circuit. So a series shunt configuration in our book is sometimes called a voltage series in other textbooks, in other sources of information. Okay, so I'm going to do another circuit now. So I'm going to do another circuit that has okay. Now this circuit. So let's analyze this circuit. So first of all, in this circuit, we are still sampling an output voltage here. So it doesn't matter how much current is flowing through our output. It doesn't matter how much current is flowing out of our op amp. That doesn't change. All that matters is what voltage this output is. So we know immediately if we're measuring a voltage, we measure the voltage in shunt. So the second term is going to be shunt. So now what happens here is we have our input is a current. And so essentially what happens is the input to this amplifier is going to be some minuscule combination. It's going to be some current flow here, some current flow here, forming the current flowing into the op amp. Now you might say, well, there's no current flowing into the op amp. Well, there's a little current flowing into the op amp, or a little. That's kind of what we're sampling here. Another way to show that we're sampling, and I guess more what we're doing is we're driving this guy to zero. Another way to describe this is that we have a current flowing into this node. This node is driven to zero by the amplifier configuration, which is going to, so this output is going to sort of produce a certain current, which is going to match this input current. But basically, the idea here is, though, that these two currents are combining to flow into the op amp in shunt. So this is shunt. So they're combining in parallel. Seems stupid. It's a little very, well, I won't say stupid, but it's confusing. It's very confusing. So this is a shunt-shunt. And the key thing here is basically if your input is a current, and another way to see if your input is a current is if your input value changing doesn't change the voltage on these terminals in the ideal case, you're probably dealing with a shunt input. And in this case, that's true. As this current increases or decreases, this input was pinned to zero. The op amp should try to pin this to zero. So these actual input voltages shouldn't change much They shouldn't change much because these currents and these currents are combining in shunt to produce basically zero. Okay, so this would be a shunt-shunt. Another name for this would be a voltage, another name for this would be voltage shunt. So, and again, that's saying we're sampling the voltage of the output, and our input is a shunt combination of two currents is the input to our op-amp. That's the way it is. So, our book would call this circuit a shunt-shunt. Other people sometimes would call this a voltage shunt. Okay, so now you might say, well, this is kind of a weird circuit with a current supply here. Not really. You've seen this before. Another way to draw this is like this. Right? So this would be the inverting amplifier configuration. Inverting amplifier is a shunt-shunt op-amp configuration. You might say, well, why? Right? Now this is confusing because now our input's a voltage. In the last case, our input was a voltage. So how do we know this is true? The test generally to do this is, does changing this input voltage actually change the voltage at the terminals in the ideal case? If it doesn't, if the input voltage changing doesn't actually change the voltage at the terminals, then it's probably not really a series input. It's probably a shunt input. And in this case, yeah, we can wiggle this voltage up and down all we want. This op-amp is going to stay pinned to basically a 0 volt. It's going to match this 0 volt reference on the positive terminal. So what we're doing really in this circuit configuration is we're generating a voltage which is getting converted by the resistor by Ohm's law, V equals IR. We're just converting a current supply. We're converting a voltage in series with a resistor into a current supply in parallel with a resistor. So we're really using this as a current supply, and we're using this current to combine with this current. Okay, so that's how we're combining them to get our 0 there. Okay, so let's look at a couple other circuit configurations. Oh. Oops, sorry. I'm going to draw this a little bit weird. Oops. Okay. So we haven't talked much about series output op-amps. We haven't seen very many series op-amp configurations. This would be a series op-amp configuration. So in this case, a series output op-amp configuration. So in this case, our op-amp is, in this case, we have a current output that we care about. So that's what, it doesn't really matter. What we're sampling here is we are sampling the current that is flowing in series with this output. So we have our output load resistor. We have a current output flowing through this load resistor. It is that current flowing through this resistor here. Maybe I should label it R. It is that current flowing through this resistor that produces this voltage here. So depending on what this current output is, this current output is what determines this voltage that comes back here. So it is the output current that determines, in this case, our output, our signal that we're using to feed back to the op-amp. So it is the output. So currents, we always sample in series. Again, we are sampling this current in series. The way we are determining how much current we have flowing out of this op-amp in this case is by putting a resistor in series with that output current, sampling that, and using that current signal to drive the circuit. So this because our output is we are measuring a current, it is the change in the output current through the load resistor that changes the signal we get. This would be considered a series. So the output is a series. And now the question is, what's our input? In this case, we have an input, which is a voltage, which should be a clue. That voltage is connected to the positive terminal. Now the question is, does increasing and decreasing this input voltage change the voltage at the terminals of this op-amp? It does change the voltage at the terminals of this op-amp. So if we increase this voltage, the voltage at this terminal will go up. The voltage at this terminal should go up if we're driving it correctly. So in fact, the input is a voltage. We are sampling in series. The input is being combined in series, right? So we are combining series combination to produce that input voltage. So this would be a series circuit. So this is this would be referred to a current series. Our textbook would call this series. Other people would call this current series because it is the current that we're feeding back on. So basically, if our load resistor changes, absolutely this signal will change. So it is the current we're sampling, and it is an input voltage that we're using to drive this. So it's going to be current series. Okay. And then the last configuration I want to show you is I'll do the book switches the amplifier configuration. I don't necessarily like that. I don't like that. Okay, so first of all, we should say when my positive terminal of my amplifier is pinned to ground, that's a good key that we actually have a current input, right? If this amplifier, if one of the inputs is pinned to ground, that means this guy is going to be pinned to ground. That means the voltage of these should not be changing. It's a good indicator. Very likely, this is going to be a current input, which would be considered a shunt input. So that's just a good first test that that's probably the case. Okay, so then we're going to have, sorry. Use the convention in the book. So now in this circuit, so again, the output is going to be it's the output current that we are sampling here, right? So it's the output current that we're sampling. So whatever this current, we have our load resistor here. It doesn't really matter how much voltage is across this load resistor. What matters is how much current flows through here, because that's going to be the current flowing through R1. We are sampling this current through R1. We are getting a voltage signal here by sampling in series. We're sampling in series with our output current. So we have connected a little test resistor in series with our current. We're using that to get a voltage signal, which is then feeding back. And actually, in this case, we're using that voltage signal. We're then converting it back into a current using another resistor. And then where that current is combining with this current, but whatever. But the idea here is it is the output current that affects the signal here. So this is going to be for sure series. And the input is a current. So the input is a current. So this should be series. How do we know the input is a current? Well, first of all, it's a current supply in this case, the current supply going directly to the terminal. The other thing we can say is the voltage, the change in input is not going to change the voltage values at these input terminals. Now, you might see this more commonly something like this. Okay, and again, we have a voltage supply input, but that voltage is being converted to a current through this resistor. So the current, it's really a current input here. And how do we tell? In this circuit, in the ideal case of this circuit configuration, as I increase and decrease this voltage, the voltage of these terminals does not change. So the voltage of the terminals does not change. So therefore, it's actually a current that we are sampling. We are combining, this current is being combined in shunt with, in series with, geez, what am I doing? This is a shunt. Sorry, it's confusing enough without me doing that. So this current is being combined in shunt with this current here. And we are sampling the output current in series, which is how we sample output currents. And that's that. So this would be a shunt series circuit. Gosh, I hope I did the last one correctly. I hope I didn't flip the last one. Yeah, this is shunt series. Okay, so another name for this would be current shunt. So current shunt would be another name for this type of circuit if you're using a book that's other than ours. So I hope, boy, I feel like I made it worse. I hope I didn't. I hope this helps the explanation. The book does, I think, a pretty terrible job of explaining this. The key thing is, if it's an output current that you're using as feedback, or the signal from an output current, then it's going to be a series as the second term. If it is a current input that you're using, it's going to be a shunt as the input term. It's weird, but that's the way they do it. And it has to do with the second term we're using refers to how we're measuring it. The first term that we're using refers to how the signals are combined at the input. So that's that. So hopefully this helped. Maybe it's another little piece of data. If you look for videos on the difference between series-shunt, shunt-shunt series, they are terrible. So hopefully this video helps somebody a little bit. Hopefully it helps. Anyway, well, thanks a lot. I'm going to leave it at that because that's bad enough as is. So we're going to leave it there. And I hope everybody has a good weekend.